Good morning, everyone. And thanks, Nectarius, for the kind invitation. It's really nice to talk here today to you guys. I'm not particularly working on urban problems, but I'm working a lot on AI and for earth sciences and climate science in general. So let me just start with my main motivation in this talk, which is about running this roller coaster. This is basically a tale in 3 acts, you will see. One on the hype of AI for earth sciences, then the kind of what I call depression, and then some hope, right? Let's finish this story nicely. So the first thing is I would like to go directly to the first act, the hype. Why are we using machine learning or deep learning or AI in general, this abuse of the term, and in particular in urban sustainability, right? So it goes without saying that AI is actually dominating many fields of science and engineering these days. You can see in these covers by Nature or Science that it is basically applied in all fields, and it is actually impacting a lot of our problems in remote sensing and geosciences in particular. It has been also advocated that by using AI and big data, you can roughly save the world and basically tackle all kinds of problems, and you can solve them. You don't have to be, these days, too smart to just download some particular toolbox, apply it. These models have been trained for classifying cats and dogs and buses and tables and chairs, and then you apply it to characterize the cities and the crops and everything. And they can work pretty well, but the thing is that there are some problems, as we will see later. Deep learning, in particular, it has been very successful for urban sustainability goals, and I would like just to review a bunch of them so you can get an idea of the possibilities of the applications that you can see out there. We have a fantastic session afterwards on deep learning applications on sustainability and urban monitoring. But first of all, what is deep learning, right? So this is basically a family of methods in the field of machine learning that they're very powerful in the sense that you will see that they are successful when 3 main characteristics of the data they convey, right? So when you have like strong correlations or autocorrelation functions, so in the sense of working with the spatial data, temporal data, spectral data, that you can find some structure in the data. And also they work very well with multidimensional data. Something that there is very important and people is starting to exploit is the use of different priors, to incorporation of different prior or domain knowledge in the algorithms themselves in the form of either designing particular architectures for doing particular things or defining new loss functions that you want to minimize, right? Well, I will give you some examples about that. Also, it is important to know that deep learning has been now democratized, so the code is there. Also, the data mostly available by ESA, by NASA. You can find data, you can find code, and you can apply it very, very easily. It is becoming not like a sophisticated tool, but more a commodity tool. And you can see this in the case of, for example, ChatGPT, right? That it is out there, you can use it, and you can do very, very nice things, right? So it is available for the wide audience and the users. And it can be used for many different problems that we are facing in remote sensing, data analysis, and in particular in urban monitoring. You can tackle problems of regression, of classification, of clustering, anomaly, or change detection, and visualization as well by means of these, let's say, generic tools. We have like these 2 pieces of work published in the last years. One is on the left, a Nature paper trying to promote the use of the combined use of deep learning and physics understanding or process understanding as the way forward. And on the right, you will see a book. This book is on, a collection of 25 chapters dealing with all the problems that we encounter in earth sciences. both in remote sensing and climate sciences and the geosciences. So you will find like a lot of inspirational developments there. There is an associated GitHub repo there where you can download pieces of code and data, so you can run some of the experiments and try to check if the models work or not. Okay, but why is that? Why is this success happening also in our field of remote sensing and geosciences? Well, basically because we are facing pretty much the same problems that we used to have in computer vision or natural language processing or speech recognition. So on the left, you have like the standard problem of object categorization or classification, cats and dogs. While on the right, we have the equivalent in Earth or climate sciences. We are maybe interested in characterizing or detecting tropical cyclones, right? So there are objects with some regularity, spatial regularity. They also move, so they have like a temporal component that you can also exploit, right? We have also some problems that we typically want to tackle in the Earth sciences, which we call it statistical downscaling, that it is basically called super resolution fusion in computer vision. So from a rough estimation of the spatial data with a limited resolution, then you want to recover the higher resolution one, right? But we have also been witnessing like a wide adoption of different methods that were originated in the field of video prediction or video encoding in short-term forecasting in remote sensing or geosciences. And also now there is some evidence of good performance of language translation models, just basically translated or adopted in the field of remote sensing of time series. Because basically you have these autocorrelation functions that I was mentioning before, right? So you have like some redundancy in time, and you have like long distance correlations that you want to exploit. So if you have simple or similar problems, maybe there is a chance to use the similar techniques or HANAs, right? Okay, for some examples on there. So now we have tools for estimating crop yield from space at a very fine resolution, so health status and productivity of corn or of crops. So that's also very nice. If you go to problems on water bodies, coastlines, and oceans, you are maybe interested in retrieving some specific parameters from space, like, I don't know, chlorophyll content or suspended matter or color. So there are many machine learning developments that they can do a very nice job there. Also, if you look at the atmosphere and air quality, here you have an example of Tropomi NO2, tropospheric column retrieval, that help us, like, you know, to characterize the air quality and livability of cities, for example. I would say that living in Paris or Brussels is not the best place to live. While here, sorry, I didn't. I got it down there. But it's in general, it's a quite decent air quality levels there. Now, machine learning is also on board, right? So you have here this example of some guys in the lab that they managed to implement an automatic detector in a constellation of minisats, so for global flood mapping. But also, you can go global, and you can use machine learning and particular generative models working with radar data for precipitation nowcasting. Recently, there has been like a wide interest in trying to replace weather forecasting algorithms. Essentially, the ACMWF algorithms have been kind of challenged by the appearance and the use of this GraphCast method, that it is a graph neural network that can actually interpolate a little bit better than the standard method that is being widely used for production of the weather forecasts. Still, there's a lot of things to do, but with more data and probably, you know, stronger computers and modern machine learning, you can tackle many of these problems at different scales, right? In remote sensing, and especially for urban monitoring, maybe we are really interested in going finer in details, right? For detecting subtle changes or subtle anomalies, for example, here. Some of my colleagues in the group, they developed a method working on multispectral data for doing super resolution of Sentinel-2 at pretty much the resolution of planets, something like that. So you can actually do this downscaling process or this super resolution, also incorporating the temporal dimension. So it allows you to better detect changes. The thing is that, okay, with finer resolution, it's fair to say that you are actually inventing details, you are inventing an image, but still you can do nice things like counting. For example, this was a case of counting buildings before and after an earthquake. So you can do things with finer resolution, even if you don't have access to this fine resolution planet data, because, well, of several limitations, and then you can work with Sentinels, downscale it, and run it, right? In the city, we have a lot of examples, right? We have a lot of examples of the wide application of deep learning, in particular for change mitigation and adaptation. Basically, I would identify like 3 main lines. One is on the try to catalyze or try to promote or to advance in the characterization of services, food service, the health, the water, the energy, but also it's quite unique advantage these days because you have access to finer and finer resolution, both in space and time. And I would like to say also that deep learning has been really proposed these days in order to advance in the estimation of some key sustainable development goal indicators for equality or energy fluxes, urbanization, even wealth or poverty has been mapped from space. Let me just review a bit these examples. Here you have an example where the authors were kind of promoting this methodology based on annotated data at high resolution. They deployed a convolutional neural network, and they could map both green and solar roof panels. They could run this large scale, so they could identify different regions that are actually adopting this technology. They can measure the kind of indicators on this deployment of the technologies of solar panels and green panels, and they can quantify that with numbers, right? With square meters and with CO2 saved. Emission saved, right? So this is one example of kind of a mitigation and accountability with a clear impact on decision making. There are some examples as well. I'm not really super confident with this one, but still, there are some examples of using deep learning or machine learning algorithms for tracking trucks and vehicles from space. Probably there are better or easier ways to do this, but they are using this for counting vehicles and roads and densities. Of course, deep learning has been used for climate change adaptation, and as I said before, there are several examples out there where you can find modules, maybe not the full model, but you can find different modules based on machine learning that can actually advance the numerical weather forecasting or detecting some floods or some extreme events, and also help in the post-catastrophe management, for example, right? So trying to locate what is the region in a particularly damaged area most affected by the extreme, for example, right? What happens with people, right? So basically, there are also very, very nice applications of deep learning in this area, mainly for describing behavior, the wealth and the health. You can find a lot of examples on this end. For example, there are some prototypes that manage to estimate fairly well the poverty from Landsat 7. Basically, you look at the structure of cities and the outskirts, and they have like distinct features, right? So they are more dense or more regular, as we saw before. And from these feature structures, deep learning managed to estimate what is the wealth indicator, right? From census data. The NASA Black Marble, for example, is a very nice repository where you can find a lot of maps for energy consumption, for conflicts as well. So this interaction between the where we live and what we do and how we live, it's really important, and this can be characterized from space as well. Also, when it comes to health, I said before this case of air quality, right? During the pandemic times, you know, these ugly, boring, dark times, we managed at home and managed to work with at this time when I see back, this development is a bit embarrassing, but yeah. It was our humble development. Basically, we took a model for predicting the R, the reproducing index of COVID-19. It was a model trained and developed for 100 cities in China, and we tried to implement it, modify it, improve it, accounting for different other variables, and deploy it in the Google Earth Engine. We could find this application that, in principle, it should give you like a prospective measure of the spread of the virus, right? After that, we know that the virus conditions and development was, triggered by many different other things, like how you live and where you actually interact with people, right? And this is far more challenging than just a simple parameter model. Also, there are examples of using deep learning and machine learning for monitoring heat and energy fluxes, and in general, but also for cities. This basically boils down to using flux towers. And in these flux towers, you can actually estimate a lot of parameters of interest, from the turbulent exchange of CO2, or latent and sensible heat, etc. And then you can correlate these measures that are, let's say, point-wise measures in the globe with satellite measurements, right? So this is, for example, a network called FluxNet. This is a sensor network of 200 something towers across the globe, and that allow us to measure carbon uptake, for example, right? And in this case, you can upscale all the measurements that the towers are actually, the flux towers are actually measuring, like CO2 or energy or heat fluxes. For that, we used MODIS in particular, but now we are working with Sentinel-2 to get a better final resolution. We extract several descriptors, liver index, some indices, and temperature, etc., and then we can correlate with the footprint of the tower. So what is actually measuring? This is just our simple regression exercise, and then you can deploy it worldwide, right? And then you can deploy as many fluxes as the tower has measured. And in this case, we are combining the three most predominant ones, light and heat, sensible heat, and radiation. And then you can start doing science from here, right? Okay, but so far so good. Apparently everything's solved, right? So we can do so many things. So wow, fantastic, right? So yeah, we can go to the beach right now, right? This is not actually the case, and you will see in a second why deep learning, even if successful, has some problems and caveats that prevents its wide use and its trustworthiness, right? Compromises its trustworthiness. Probably you know about this story of Microsoft Tie, right? This was like the early version of ChatGPT. It was a chatbot, and they deployed it in Twitter, and then in just a day, 24 hours, it became Nazi. Just interacting with the data that observed, right? With the interaction with the people, it turned to be like very, very easily sexist and racist, okay? So this is a problem. A problem with automatic machine learning is that it is actually inheriting, it is actually embedding all the biases that are encountered in the data, right? Maybe you are also aware of adversarial examples. An algorithm trained for classifying pandas and bears and dogs and cats and everything, maybe it's quite accurate and identify that panda on the left, but if you just add a particular noise level and noise source on the image, not perceivable, then the classification turns to be completely crazy, and it predicts given here, which is a kind of wonky. The most annoying thing is not the prediction, but the confidence level. Right? It says that this is a given with that particular confidence level. This is really annoying, right? So you can not only be right for the wrong reasons, but being wrong for the wrong reasons as well, right? So now this is actually what we call hallucinations in machine learning or deep learning. If you go to Wikipedia, you will find that hallucination is basically give a confident response that it is not actually justified by the data that you have been using for training. You find this example on ChatGPT, for example. You are asking, summarize this article in the New York Times, and the ChatGPT answers, well, this is the summary. It is very confident, right? It's very assertive. The only problem is that that article does not exist. So that not only happens in language, but it also happens in images. In here, some authors, they deploy this deep learning-based fusion algorithms and detection of different areas and cities, and they saw that there are some classes that pop up that they did not exist in the labeled data set. So how can you do policy with predictions that are meaningless, right? So they don't even exist in the training data set. So there are new invented classes. So this is quite worrying. Yeah, and what happens with the context, with the composition? We said that deep learning is very efficient because it actually extracts patterns, right? Spatial and temporal patterns, but it has no sense of context, of composition, or even of semantic meaning. In this case, they trained the algorithm for detecting ships. It is very, very correct and very efficient in detecting these ships, right? Because it recognizes this sort of ships, right, in the training database, but has no sense of what a ship is, right? So all the rest are not ships because they don't have the same shape, right? Maybe more worrying is about semantics. You can prompt, okay, generate an image of an astronaut riding a horse on the left. That's nice. You change slightly the sentence, right? Meaning the same thing. I mean, keeping the semantic meaning. Horse rides astronaut, and it generates the same thing. So it has no sense of semantics whatsoever, just about predictability, let's say, or fitting. But I would say that more worrying is about the thing that deep learning has no sense of physics or causality. On the left, generate a coffee cup with holes. Yeah, it makes something realistic, but actually the actual mass or energy conservation or fluid condensation is not actually preserved. This happens also in weather and climate models. And on the right, you see this algorithm that says that the seagull caused some damage here because it has no sense of what a gravity law is, what is cause and what is an effect, right? And this is really, really worrying, all these things, right? So can we trust these machine learning algorithms when you are deploying that for urban sustainability in particular? It's a bit compromising, right? But the good thing is that there is some light at the end of the tunnel. There are some developments out there that can help us to try to mitigate these problems, okay? So let's go for Act 3, the hope. I subtitle it like integrating causal knowledge in machines. This is the way to go, in my opinion. And there are different ways that we can do that. Basically, as a summary, we have seen that there are like 3 main problems right now in machine learning. The first one for us, working with geosciences and climate, models do not respect the most fundamental laws of physics like mass or energy conservation, and this is quite worrying when you are trying to do statements about that, no? The second one is that we don't know what these big fat neural networks have learned, and we want to know, because you know, models, if they're accurate, they should be also accountable, why you are predicting this or that. And the third one is about the cause-effect relationships that you never know if they are actually learned or not. I mean, you can train a model for predicting Y from X or X from Y, and then probably you will get more or less the same accuracy, but yeah, what's the point? I mean, probably they have not learned, these models have not learned what is a cause and what is an effect, right? So all these problems have rise to a very exciting fields. Physics-aware machine learning, explainable AI, and causal inference. I will try to review what are these fields, and I will give some examples of applications. So this is machine learning, okay? Are we on the same page, right? So you want to learn a function that takes some data and spits out some other data Y. The good thing and the difference between machine learning and statistics is that this F function is typically non-parametric, is non-linear, and most of all is learned from data, okay? From pairs of data, X and Y. And this is the big difference. This is physics-aware machine learning. So essentially, it's the same thing, but if you know the Navier-Stokes equation actually serves a purpose and helps in solving your problem, maybe you can incorporate that domain knowledge in the algorithm to make it more consistent with the physical knowledge, right? You will find different names for this. People call it physics-aware, machine learning, physics-guided, science-guided, physics-informed, but are all the same flavors of algorithms. Basically, in this little paper, you will find it in archive. We basically propose like 4 families of methods where physics and machine learning can interact. On the one hand, you have models that can merge, can blend data and models, and machine learning models. You have also other techniques that we call emulators or surrogate models that basically try to replace a costly physical model with a machine learning algorithm. The third family is learning to parameterize some problems, some estimates of parameters and distribution of parameters. And the fourth one is a very exciting new field called learning laws or learning physics from data. I will try to give you some examples from that, right? So in the first case, the hybrid machine learning approach is basically a formalization that we propose in this paper, where we just want to use the same architectures of neural network, but if you know something about the physics, maybe you can design a particular layer or a particular loss function that actually improves the consistency. In this case on the right, you will see an example where the authors wanted to use deep neural networks for predicting the motion field of some particular climate variables here. So they used a deconvolutional network, and then at the end, the last layer, after the prediction of the motion field, they ingested some physical warping model that could actually modify in a meaningful way or sensible way the predictions of a neural network. The good thing is not only that, the good thing is that now we have this capability of training end-to-end, whatever architecture. So the authors learn not only the parameters of the neural network, but also some of the parameters of the physical model, which typically they are, kind of hand-waving tuned or, fixed a priori, right? But you can learn that from data. The second family is what I told you about, okay, let's replace a physical model, a costly one, with a machine learning algorithm. This is just a simple regression problem. So you basically take all the simulations that you can afford. In this particular case, we wanted to emulate Motran, which is a very powerful model especially used in atmospheric sciences. And we replace Motran with machine learning algorithms. We tried different methods, Gaussian processes, neural networks, random forests, of course, etc. And you can see that in this case, GPs, Gaussian processes, perform best. They provide also, meaningful sensitivity analysis rankings, let's say. So what are the wavelengths that are more important for every parameter of interest? But also not only that, the sensitivity, but also confidence intervals for the predictions. And at the fraction of time. I mean, instead of running for every pixel you spend like 20 seconds or something, you can run the emulator in milliseconds. Good. And now the exciting field of discovering physical equations from data. There are a lot of algorithms out there. This is a particularly useful and simple one called Cindy. In Cindy, basically, you transform the problem of discovering a differential equation from data with a problem of regression or sparse regression. So you hypothesize a basis functions, a lot of bases, and then you want to select which ones are the most plausible ones, right? We have used this method for trying to characterize the dynamics of different ecosystems. In here on the right, you can see that some ecosystems and the dynamics, right? So their evolution through time. And well, the algorithm will tell you something like that, a solution based on ordinary differential equations, which is good for interpretability of what you have what you see, but also because looking at the coefficients of the differential equations, you can say something about the dynamics, the bifurcation points, the stability, the chaoticity, right? So you can see something about the system just by looking at data. And then the fourth one is about parametrizations. Basically, we are most of the times confronted with this problem of forward and inverse modeling. You have state variables, and you have a model that gives rise to some, let's say, observational world data, and then you want to retrieve these parameters, right? Or the distribution. That would be ideal. The thing is that in this particular work, what we aim to do is to combine both the model, the RTM, with a neural network going in the inverse direction, right? So the thing is that if you treat this as a Bayesian inference problem, that turns to be really, really complicated because you want to put a very complicated problem, a very complicated code, the RTM, as a mean of a Gaussian, right? So then you want to estimate the inverse of that. So that turns to be super, super complicated. But finally we managed to do so with variational inference, and you can retrieve parameters and their distribution from the observations, right? Okay, so there is some hope when it comes to make models more consistent with what we know of physics. Let's see what happens if you want to stick to big fat neural networks and you want to learn something about that, no? Learn something about your exercise. This is called explainability, okay? And there are different ways, different families. Explainability in a nutshell is illustrated in this very nice figure. Essentially, you have a neural network that can characterize extreme events, for example, and it can tell you, okay, these are the characteristics associated to a volcanic eruption or not, and then maybe you want to ask questions, right? So what are the features? What are the relevant features that you are actually looking at, right? And you have different ways. I mean, you have different scenarios. For example, you have scenarios where the network is wrong, and it can tell you that this is not a volcano erupting, but it is a potato. Okay, that may happen. And then you want to ask, okay, what are the features driving that decision, right? Which are the filters that the network has learned that gives that wrong decision? Or maybe you're right, and then you want to learn those as well, no? There are some methods for doing this scrutinization, this analysis of the neural networks, and not one or two. There are hundreds and hundreds of explainable AI techniques, but essentially, in a nutshell, you will find these very nice reviews out there. Finally, I would say that there are 3-4 families. One family is that of developing models that are explainable by construction. So if you manage to identify different sub-problems in your problem, maybe it is smart to dedicate small resources, smaller models for each one of them, and then combine them all. So by construction, you can see something. There is another field that it basically says, okay, I have my big network, maybe I can replace it with something simpler. It's like doing emulation on a machine learning model, right? So you learn, for example, a decision tree, which is a very simple thing, to mimic the decisions of a neural network. And then the decision tree, okay, maybe you lose some accuracy, but you gain in interpretability, right? And there are other techniques like sensitivity analysis that I would like to show you something about. Sensitivity analysis is basically a family of methods that try to distort the input data, so the input features, and see how this distortion affects the output, right? So this is a very old technique from the 80s. And now it has been like improved in many different ways. I would like to show you an example. Please, if you can actually turn on the video. Here you have a video of an algorithm trained for detecting anomalies. So we are here working on an unsupervised case. The method was trained on 10 years of data. Here we are showing some data in the year 2010. And the algorithm is only working with temperature anomalies here. So it is actually focusing on different regions, right? These are the blobs, the anomalous blobs, and it actually starts to screen this out and finds that this particular period of time, around June, July, August, something like that, something happened in that region, Actually, you can just take a look at that. You can eventually you can delineate that region. You can characterize that region, area, perimeter, whatever. And this actually corresponded to the 2010 heat wave in Russia that caused a lot of casualties and a lot of damages in crops, right? So this is cool. We can do this. Nice. But what are the drivers of that decision? I mean, we are going to be implementing policies, right, around this that have a lot of societal, environmental, economical implications, right? So we need to have models that are accountable. And in this case, this is extremely complicated because it's an unsupervised algorithm. So we cannot perform kind of, attribution of features on this and that. But we can resort to this explainable AI techniques. In particular, we used integrated gradients. And we devised this network. This is an encoder-decoder neural network where we are ingesting different variables, not only temperature anomalies, but vapor and GPP and transpiration, etc. We learn the dynamics and the spatial temporal correlations in the encoder that gives rise to a latent representation, and when this latent representation is decoded, you are able to reconstruct well the inputs, right? But moreover, we want to use this latent representation and summarize this in numbers that reflect the anomalousness, right? An anomalous score. The thing here is that we are not using variational autoencoders, but just plain autoencoders, so the latent representation is not necessarily Gaussian, so it is a bit compromising to use that directly as an anomalous score. So we implemented a Gaussianization step there. So we Gaussianize this latent representation, and then we apply the minus log of p, and then you come up with an anomalous score, right? So actually, on the bottom line there, in the bottom figure, you can see that well, more or less, the Russian drought is actually well captured, and this is kind of okay. I mean, we saw that in the video with just temperature anomalies, but here we want to learn more, right? And in this case, this is an unsupervised scenario, and we have to take a look at what is actually the decoder encoding, right? The encoder encoding, right? So we can do this with sensitivity analysis or integrated gradients, and this is really cool because you can see directly what are the features that are contributing to this score in time, right? And you see there, like, I don't know, for example, temperature at 2 meters and also vapor, they have a positive score around the time where this heat wave occurred. But this was kind of expected. The interesting thing is to look at the negative values, right? At the minus point there, and you can see again that there is temperature, but like a month and a half before the event started, right? So this is very useful for anticipation of events. So take a look at this variable, or for example, deficit in moisture. There were already triggers like 1 month, 2 months before the drought happened, okay? So understanding, I think it is crucial here. But if you want to understand, please do not use like an ad hoc causal model like in neural networks. In neural networks, the inputs are causing the output, right? So you are assuming a very restrictive causal model, even without knowing it. Because the different dexes, the different input variables, they are already related, and they are also causally related, right? But you're assuming only one direction of the cause-effect relationships, right? So this is the field of causal inference. We'll give you some examples about that. So essentially, there is no formula for this, right? So you want to use as much data as possible, and then you want to spit out like causal graph. So yeah, we want to learn which one goes first, and what are the relations, and when these relations happen, right? So I'm not going to bore you with sophisticated maths and top books. Probably this is the best book to start with. Probably, I don't know if you guys have read it, but I strongly recommend it to you. The Book of Why by Gustau, and he's promoting this way of these different rungs of causal inference. So the first rung, the first step is association. This is what deep learning is doing, or machine learning in general. So basically answering question of what is this, what is that, seeing. right? The second one is on interventions. It's about doing, is what would happen if I do this, right? So I intervene in that variable, that should change the other one, right? And the third one is, the third one is not actually covered, well, partially covered in this book, but then you have this other book by Miguel Hernan that basically it's on counterfactuals. What happens? What if I had done this thing? So this speaks a lot to, you know, interventions, counterfactuals, and what if scenarios. So you go from the deep learning world to an interactive world to evaluate different scenarios. And I think these two latest rungs are really important for evidence-based policymaking. No? No worries, there is code for doing this. There are toolboxes, right? So you just upload your data, then click, 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 and then you will find some causal graphs, some causal models. We have developed this platform in Valencia. It's called Cosmi, cosmi.net. You can try it out. And you will find two evaluation systems. You can evaluate your causal models, but you can also upload your data, and the model trains different causal discovery algorithms and will return to you a family of possible solutions where you can interact with. Yeah, probably you know this, right? You're working in urban environments, right? So William Shakespeare already said, hey, don't worry much about the buildings, but worry about the people, right? So let's see what happens with the people. People is moving, people is migrating because of climate change. So let's see what we can do with machine learning or advanced causal inference in particular about that. And in particular, when dealing with disasters, no? Disaster management boils down to answering some causal queries. And this has been hypothesized several decades ago already. The science of causality should be the science of answering what happened and what would have happened if I did something else when it comes to natural disasters, right? Understanding disasters, as I said, is basically answering causal questions. And you can answer in different ways. You have the field of causal discovery. So given some data, let's say some time series, you want to discover what is the cause, what is the effect, right? And what are the time lags occurring in there. And then you have the field of cause-effect estimation. In cause-effect estimation, you want to quantify the impacts of an intervention, right? Or a change in one variable, what happens with the others, no? I will give you a couple of examples in each one, discovery and estimation. Plenty of methods, like hundreds of methods for doing causal discovery, hundreds of methods for doing cause-effect estimation. No worries, some of them they're already implemented in the toolboxes. Let me just jump directly to the first one. An example that I think is pretty relevant in current times because of climate change is actually exacerbating the migration patterns and also the internal mobility and displacement of population. This is an extremely complicated problem because it involves climatic variables, societal, economical variables, migration patterns that are really difficult to account for. And there are some myths as well, as you will find in that Nature Climate Change paper, that they basically advocate for more, let's say, lot of analysis of the data and also with more advanced methods, not just association methods like regression algorithms and stuff like that, no? But more towards causality. We focused here in the Horn of Africa that has suffered like vast drought events in the last years with a lack or a scarcity of water and food, and it is forcing a lot of migration patterns. So how did we tackle this thing? Well, we go like district by district in Somalia, and we extract all kinds of variables from remote sensing, from environmental reanalysis data, socioeconomic data, etc., food prices, livestock prices, water prices, all kinds of variables, precipitation, also conflicts, right? The interaction between society and the environment is really relevant here. So, yeah, our target variable here is what we call the drought IDP. IDP stands for internal displaced population, right? And we want to learn a causal graph per district because There is not a common causal graph for every migration pattern, but they're especially located and also temporally evolving. So these are more or less the features that we extracted, and then this is the result of a particular algorithm that we used. It's called PCMCI, that it allows you to extract from time series this causal graph. You will see that there are some colors there, so about the relevance of the variables, and also there are some arrows identified, right? So the causes of our target here on the right, the drought IDP. But also you see some numbers, right, on top of the edges, and these numbers are the weeks that are lagging the cause and effect, right? So this is very, very useful for identifying which are the real causes of IDP. In here, you see, for example, that SPI, the precipitation, is really important. And after 2 weeks, the model learns that a migration pattern, a migration burst is actually occurring. There's also the water scarcity after 4 weeks, a month or so, that triggers these migrations. And now you can be fine like this. Okay, I have an explanatory model, completely transparent, completely accountable, and you can do 2 things here, from here. You can do intervention analysis. What happens if I modify this? What happens if it had rained more? Or what happens if I provided more money for food or more money for livestock or whatever, right? And then quantify how many people who have stayed in the same place. Or you can be maybe interested in anticipating and forecasting these patterns, right? So this is quite different to what one would do with machine learning. In machine learning, you would basically take all the features, feed it to a random forest potentially, and then predict the IDP, right? In here, we have this opportunity of looking at the real causes, the causal patterns of IDP drought. And this is what we did. And what happens is that if you use causal features, you have a causal forecasting model, that it is more robust, essentially when the displacement happens. You only have to compare, for example, in this big event of migration patterns, you can compare the red and the cyan one, and you will see that there is actually capturing much better these patterns. Okay, this is one example. The second example, also in the same area, is about humanitarian aid and impacting the food insecurity. Just some numbers. The region is actually devastated this year, and after several years of continuous droughts and lack of money of the humanitarian aid by the rich north, they are suffering a lot in acute malnutrition and migrations. And this is happening now, and probably it will be devastating this year. So what we wanted to do here is try to understand what are the levels of humanitarian aid that can actually, compensate or alleviate the situation, and give numbers to that in a kind of, fair manner. So basically, we went to the region. We took some data from the last 5 years in the most impacted districts here. And we collected all kinds of market, food, livestock, water prices as well, fatalities, climate variables of all kinds of humanitarian aid in dollars. And the target was malnutrition. And instead of working with causal discovery, which is, in this case, is very compromising because in the end, we have only very short time series of 70 points, right? So this is almost impossible to learn something meaningful from there. What we did is to suppose a feasible causal graph like this one. We interacted with experts in the field and they say, okay, it makes sense. So we assume that, and then we interrogate, we query the causal graph with data, okay? So this is super, super easy to do, and for that we just used least squares, ordinary least squares regression, and also lasso regression. So we developed a lot of regression models for interrogating this and fitting with data, and then we obtained kind of a decent correlation score here, R square And then more important than that is that you can take a look at the coefficients and you can learn something. You can say, for example, that the high values of livestock and water prices are the ones that are actually impacting most the malnutrition indicators there. Okay, so that's everything that I wanted to say, and I would like to just end up with a take-home message. So fitting, I don't think is enough, right? We need to understand. And here I put like 3 interesting statements. Probably you know some of them. You can be right for the wrong reason, right? And then that advocates for the use of more thoughtful algorithms based on explainability and causality. All models are wrong, some are useful. Maybe that is triggering the question of, are our models consistent with what we know? Are they incorporating domain knowledge or not? Are they consistent with what we expect? And AI is not deep learning, dude. So yeah, AI is more than just fitting, okay? So thanks very much for your attention.